We've considered the major planets, the 8 major planets, and we've seen Pluto got demoted out of that to a minor planethood status. So let's look at the rest of the objects in the solar system. Asteroids, for one thing. Thousands of them have been discovered. They're small, rocky, and metallic, small compared to planets and moons anyway, for the most part. They're leftovers of the formation of the solar system. Jupiter's gravity keeps them stirred up, and that prevents their coalescing into a single object. They are not the remains of a destroyed planet. That's a common myth. If you combined all of the asteroids into one object, it'd be less than 4% of the mass of Earth's moon. Most of them orbit between Mars and Jupiter in the asteroid belt, although there are asteroids all over the solar system. That just happens to be the most crowded place. Some are on orbits that cross Earth's orbit occasionally, and they're the oldest rocks in the solar system. Every once in a while, a piece of an asteroid will land on Earth, and we can use radioactive dating of the isotopes in it to determine its age, and they're about 4.56 billion years old. We don't have rocks that old on Earth, or at least not on the surface of the Earth, because we've got erosion. Anything that was that old would long ago have been washed away by rain and weathered and washed into the ocean, more or less, or turned into soil somewhere. Here's a picture of the asteroid Gaspra. This picture was taken by the Galileo spacecraft in 1991 when it was on its way out to Jupiter. Galileo orbited Jupiter for quite a few years, the spacecraft that is. And note the odd shape of this. Few asteroids have enough mass to form a spherical shape. It takes a certain minimal amount of mass so that the self-gravity will crush in on things, kind of soften and dissolve the inner parts and make it spherical. But these things aren't massive enough for that. Here's the Eros asteroid. This was a picture taken by the NEAR spacecraft, and that crash landed deliberately on that asteroid in 2001. I don't remember the name of this asteroid, so sorry about that. This is Ceres, which is the largest asteroid, and it alone accounts for 1/3 of the mass of the entire asteroid belt. But its mass is only about 1.4% of the mass of the moon, so not much to it. The bright spots on here are sunlight reflecting off salt deposits, but not just table salt. There are lots of other salts you could possibly have. And when they first saw this, there were news reports in certain less than reputable publications that said that the inhabitants of Ceres were warning us away from it, and turns out they were just sunlight reflecting off salt deposits. And this picture was taken by the Dawn spacecraft, which went into orbit around Ceres in 2015 and is still in orbit around Ceres. It ran out of fuel though in 2018, so its mission life essentially ended then because it can't align its antenna with Earth anymore to send information back to us or receive directions from us anymore. So it's just a dead spacecraft orbiting Ceres. So where are those asteroids? We can check out a picture here of the current positions of planets and asteroids as of June 5th this year. So at least I think that's the date on here. It's hard to read. Lots of stuff here. That's the inner solar system. And a few things. Mercury's orbit is the innermost blue circle on there. And then so it would go Mercury, Venus, Earth, and Mars on here. So Mars is the outermost blue circle. I kind of missed with the arrow, but you get the picture. The red circles on here, both the filled and the empty ones, have their perihelia closer than 1.3 astronomical units. And perihelion is closest approach to the sun. And Mars orbit is the outermost blue circle on here. Beyond that somewhere would be Jupiter. All those green circles have their perihelia farther away than 1.3 astronomical units, but you can see not all the asteroids are in between Mars and Jupiter because there's quite a few. There are some that even have their orbits inside of Mercury's. Lots of them around Earth. So that's a somewhat sobering note. Here's a bit more of the solar system. On this one, the outermost blue circle is Jupiter's orbit. So Mars orbit is the inner circle in here, and then this is Jupiter's orbit out there. So most of the asteroids are in between those two, but not all of them for sure. There are groups of asteroids that orbit in Jupiter's orbit. Jupiter is located just about down here at the bottom right now, and you can I can see a circle here, but you probably can't. But there's a group of asteroids in front of Jupiter in its orbit. They're centered around a point about 60 degrees in front of Jupiter, and then there's a group about 60 degrees behind Jupiter as well, and those are called Trojan asteroids. And Jupiter isn't the only planet that has Trojan asteroids. The other gas giants do as well. And when we see a plot of the outer solar system, you'll see some in Neptune's orbit. So there's the outer solar system. Or actually, that's the inner solar system, excuse me. The green circles have perihelia greater than Mars orbits. So you can see there's a whole bunch of them. I was just on the Minor Planet Center tonight when I was updating these plots of the asteroid positions and saw this information there. Near-Earth objects discovered. These are asteroids for which their orbits cross Earth's. This month, 42 new ones. We're only a week into the month, and 40 new ones. This year, 1,168 near-Earth objects discovered. All time, about 26,000 near-Earth objects. And then minor planets, this includes asteroids, Kuiper Belt objects, which we'll learn about soon, and other things. This month, 43 of those discovered. Over 1 million minor planets discovered over all time. And this would stretch all the way back to 1800 when Ceres, the largest asteroid, was discovered. No new comets discovered this month, but there have been 26 discovered this year. They're not all going to be spectacular. Most of them are things that you need a pretty good telescope to even spot as a faint fuzzy. But anyway, quite a few discovered of those. Okay, here's a film playing tag with an asteroid. NASA had a spacecraft that rendezvoused with an asteroid and grabbed some material from it. It's going to return it in a couple of years, but this had the most convoluted name. OSIRIS-REx is what they called it, and you can see what that stands for. NASA does this all the time. They somehow work a bunch of words about whatever it is the thing's going to be studying into a single word. But anyway, it briefly touched the near-Earth asteroid Bennu, and it grabbed a small sample of material for return to Earth, scheduled for September 2023. They grabbed about 60 grams of material, which is not much. Every morning I make coffee, and I use 3 small scoops of coffee, and I actually weigh it on a scale, so I use the same amount all the time. And for making my morning coffee, I use about 33 grams of coffee beans, which is only 3 small scoops of it. So if I had probably 5 small scoops of material of this asteroid, that's how much it'll be returning. And the speed when this thing impacted was less than 4 inches per second. And if you multiply that by a minute, you do 60 times 4, 240 inches in a minute, which is only about 20 feet. So if you were walking across the front of a classroom, you wouldn't even get all the way across the classroom in 1 minute of walking. That's how slow this thing was going when it hit. But look what happens when it strikes the asteroid. Okay, here's Tagging Bennu, the movie. It's a blockbuster hit. And it's orbiting around for a while, trying to select a good landing spot so it doesn't destroy itself on landing. Looks like a pile of rocks. Not very tightly held together either. Getting closer. There's the shadow of its grabber arm. And it just hit, and look how that stuff flies off there. 4 inches per second at a snail's pace. And gravity is so weak on this asteroid that stuff flies all over the place. That was pretty neat. So that's a bit about asteroids. Interesting things. More solar system objects. Comet. They're often called dirty snowballs, although I heard a few years ago they had one that I think they thought was more dirt than snow, and so they called it a snowy dirt ball. But you have to let your snow include not just water ice, but also frozen carbon dioxide, methane. Methane is CH4, ammonia is NH3, and some other things. And the ones that do visit the inner solar system are usually on very elongated orbits. And so their orbits have high eccentricities, which is a description of an ellipse, and that means they're very long compared to how wide they are. So a very stretched out ellipse is what they usually are. Their tails form as they approach the sun. When they get closer to the sunlight will vaporize the ice on the surface of them. The ices don't usually pause in a liquid state. They just go from solid to vapor, and that stuff will evaporate as it nears the sun, and it'll expand away from the comet, carrying away some of the dirt with it, and then a tail forms. The material that has evaporated off the comet is pushed away from the comet in the direction away from the sun by the solar wind, which is a wind of particles, mostly protons and electrons, that blows outward from the sun. And so that's what forms the tail, is that stuff evaporating off of it. And we can sort comets into 2 major categories, which we will do soon. Here's some pictures of comets. I'm pretty sure this was Comet Hyakutake, which was visible in 1996. I thought that would be the brightest comet I'd ever see in my life. At its close approach, you could see its tail from the Walmart parking lot, which was pretty darn amazing. This is Comet Hale-Bopp, which was discovered, I think, the summer before Comet Hyakutake simultaneously on one night by 2 different amateur astronomers, Hale and Bopp, who both discovered it at the same time. And it had its closest approach the year after Hyakutake in 1997, and it was even better than Comet Hyakutake. You could see its tail from the Walmart parking lot, but it was even longer and brighter. So this is a comet that came by in about 2007, if I remember correctly. It wasn't very spectacular for a northern hemisphere observer. This was Comet McNaught, was the name of it. The one time I saw it was shortly after sunset, and I had to be looking west with a pair of binoculars, and I could just barely see it in the glow above where the sun was setting, and then it set too. But for the southern hemisphere, it was pretty spectacular, and this was a picture taken from one of the cities in New Zealand. So pretty amazing sight on there. The 2 categories we split comets into are short period comets, and these are comets with periods less than about 200 years, and the upper limit on these is somewhat arbitrary. It's just a round number. They tend to orbit in the same direction as the planets. If you go way above the north pole of the Earth, they'll be orbiting in a counterclockwise direction. Their orbits lie within about 30 degrees of the Earth's orbital plane. About 100 of them have been discovered so far. Probably the best known long period or short period comet, is Comet Halley. Interestingly enough, Comet Halley is one that orbits in the direction opposite the planets, but it didn't used to. We can trace its orbit backwards, and astronomers discovered that on a few orbits back, it had a close approach to the big disruptor, Jupiter, and Jupiter flung it into an orbit where it's now orbiting opposite the direction of the planets. And so you can blame Jupiter for that. Then there are long period comets, and these orbits are longer, usually much longer than 200 years. They don't have any common tendency for their orbital directions, so they're as likely to orbit the same direction as the planets as opposite the direction of the planets. They don't have any common tendency for their orbital planes. They don't tend to lie within 30 degrees of the planetary orbits. They'll come from any direction, random, more or less. And hundreds of these things have been well studied and a lot more discovered. Some famous examples of these recent ones are the Hyakutake, Hale-Bopp, and McNaught. So the ones that we showed pictures of here. Okay, the Kuiper Belt, proposed as a source of short period comets. Well, why do we need a source for short period comets? The thing is, they are temporary objects. With every close approach to the sun, a significant chunk of their material evaporates away. Maybe it's a few percent, maybe it's only 1%, but they don't have real long orbits. Comet Halley, with a period of 76 years, in only 7,600 years, it'll complete 100 orbits, and it may not even last that long. It may have evaporated away all of its evaporatable material in 100 orbits. 7,600 years is nothing compared to the age of the solar system. So people proposed that there must be a source of these things out in space somewhere, probably beyond the orbit of Neptune, and if we look out there, maybe we'll find something. So this is going to be a donut-shaped region that's beyond Neptune's orbit, and it's part of a larger group of objects out there called trans-Neptunian objects, and that just means beyond Neptune. Ranges from about 30 to 50 astronomical units from the sun. The semi-major axis of Neptune is 30 astronomical units, or just about that. So, and it was an untested hypothesis until 1992, when the first object in this region was discovered, and I put first in quotation marks because it was actually the second object in this region that was discovered. The first object in this region was discovered in 1930 and got so much publicity that it was named a planet, and was a planet, considered a planet, for about 75 or 76 years when it was demoted to minor planet status. And of course that object was Pluto. Pluto was the first object in the Kuiper Belt discovered. Since 1992, we've discovered a few more objects in this region. And just to show you, let's check out the outer solar system. Whoops, can't click to it, but it is on the next slide. All right, here's the outer solar system, and the blue circle that's on here, the outermost blue circle, is Neptune's orbit, and then the one inside of that would be Uranus's orbit, and then Saturn, and then the innermost blue circle here is Jupiter's orbit. So we don't even see the terrestrial planets on this thing. And these red objects on here are Kuiper Belt objects. thousands of them have been discovered so far. Okay, this plot was from May 13th, 2019. So, but I think I looked at the most recent plot, and it doesn't look a whole lot different from this. Some of the objects on here, I think I've got them identified on here. This is the solar system out past Neptune's orbit. You can see Jupiter's orbit way on the innermost part there, and then Neptune's orbit, the outermost circle that's shown on here. And the white circles are Pluto's siblings. These are things that, just like Pluto, have a 2 to 3 orbital resonance with Neptune. And what that means is, for every 3 orbits that Neptune completes, these objects complete 2 orbits. That's the group that Pluto fits in with. And Pluto fits in very well with other Kuiper Belt objects. Similar densities, they're mostly ice, very dense, hard ice, but mostly ice. Some rock, not a lot, but some. That's what Pluto fits in with, and it's one of thousands of objects out there. So don't feel bad for Pluto getting kicked out of the Planet Club. It's always been part of a much larger tribe that's out there beyond Neptune. More things about the Kuiper Belt. Kind of like the asteroid belt, but larger. 20 to 200 times as massive. So there's a lot of material out here. And things out here are mostly ices, methane, ammonia, water, and other things that can form ices. Whoops. Most of the discovered objects out there in the Kuiper Belt are stable, and they're probably not the sources of short period comets, because you need a somewhat unstable orbit to do that. But we've discovered thousands of things out there, and the reason we haven't discovered more is, for the most part, because we haven't looked. Somebody needs time on a major telescope to study regions out here, and when they get that time, they discover things. But once they've discovered a few thousand of them, it's not exactly high priority to give telescope time for a search out there anymore. And so the pace of discovery has slowed just because the pace of looking has slowed. Then there's other trans-Neptunian objects. There's something called the scattered disk. And these are things that are thought to have been tossed out of the standard Kuiper Belt with gravitational interactions with mostly Neptune. And their makeup is similar to the Kuiper Belt objects, ices, rock, some rock, but their orbits are more elliptical, and their near points might be 30 to 35 astronomical units, but the far points are well beyond 100, so those are very elongated orbits. It overlaps with the Kuiper Belt, though, and that's most likely where short period comets come. On some of their closest approaches to the inner solar system, when they're around 30 astronomical units, if they've got a near rendezvous with Neptune, Neptune's gravity may grab them and fling them into the inner solar system. So, then there are over 200 objects in this scattered disk that are discovered so far. Okay, our last group of solar system objects here, and this is called the Oort Cloud. The Kuiper Belt was named after Gerard Kuiper, a Dutch astronomer. The Oort Cloud is named after Jan Oort, also a Dutch astronomer, and it's a spherical region, spherical as in ball-like, and it's hollow in the center, but it surrounds the inner solar system. So it would be like, sometimes you can get these oranges that have super thick skins, and you can peel those off in one piece a lot of times and sort of put it back together, and you'd have a hollow orange. Well, the Oort Cloud is kind of like that. It's a hollowed out sphere that surrounds, when we say inner solar system here, we're including the Kuiper Belt as part of the inner solar system. It's a long ways out there. The inside edge of it is 10,000 astronomical units from the sun, and the outer part about 100,000 astronomical units. 1.6 light years is a little more than a third of the way to the next nearest star. So this really expands the solar system. And it's encounters with passing stars that can send objects from this region toward the inner solar system. Okay, we don't think about this a whole lot, but the stars are in motion. The sun, our solar system, is orbiting the center of the Milky Way. It takes about 200 million years, or a little bit more than that, for an orbit around the solar system. And all the stars around us are doing the same thing, and they don't have perfectly circular orbits. Their distances between each other vary, and if they get close to each other, they may grab objects from another star's Oort Cloud, or we may grab some of theirs. They may get their orbits disrupted and get flung into the inner solar system, and we've got a new comet Hale-Bopp or Hyakutake or McNaught. That's what can cause those things. Now, so far, the Oort Cloud is just a hypothesis. The things out here, they don't give off their own light. They only reflect light. Since they're so far out there, something 10,000 astronomical units from the sun, they would get 1/100 millionth the amount of light that the Earth gets. And that's what they have to reflect back to us for us to see them. So they're going to be hard to see. But we're building bigger telescopes that are more light sensitive, and so higher light gathering powers, so maybe someday. If you're interested in this kind of stuff, there are Wikipedia articles on the Kuiper Belt, the scattered disk, and the Oort Cloud, and this is probably the best place to get up-to-date information on it, is to check those out. All right, we have finished the solar system. It's not just the sun and 8 planets. It's the sun, 8 planets, a whole lot of asteroids, and the Kuiper Belt and the scattered disk, and probably the Oort Cloud, although the Oort Cloud is just a hypothesis at this point. We haven't verified it yet.